material. Isotropic material, that means the E, Poisson ratio nu, and all other material properties are not a function of the directions. Okay. So for example, here the Young's modulus describing the material in the x direction will be the same of the Young's modulus describe the material behavior in the y direction. So that is the independent of the directions. So with this one in place, then we can begin to describe. So now again we apply the superposition principle to do this one. So here again, if we consider this is a material and this material is the deformable object. Okay, so for example, if this deformable object, if we place into the coordinate systems, for example, this is x and this is y, these are xz, xyz coordinate systems. And this is a deformable object. For example, by superposition principle, we can decompose a general loading into three components. One is the loading in x directions. So let me use the color. So for example, if we are able to decompose the loading into x direction, let me call it fx. And the loading into y direction, let me call it y. And the loading in the z direction, let me call it fz. Okay, then this loading should be in static equilibrium. So that must have the counterpart in the other side. Okay. So everything we talk about is in static equilibrium. So this one we can decompose into the superposition of three scenarios. One is in x direction, y direction, z direction, and plus I'm running out of the space, so I need to put a smaller. X, y, z plus. Sorry, would that be too low for people to look at this one? Okay, so that's the loading applied individually. Here we have done certain steps, which means we analyze the loading conditions, and then we'll be able to find the components of the loading in x, y, z direction individually.
Those supposed to be FZs.
F, y, z. So here should be FZ. Thank you. Yes. Okay. So now we can decompose further the components, which means the F components only. So that means here this is in the F directions. Okay. So that is the F of x. And furthermore, the f of x that divides the corresponding cross sections, actually that will give us stress. So here, I want to say is the corresponding, the force divided by the cross-sectional area that will corresponding to is a normal stress. Let me get the sigma x. So again, this is the axial stress, which means right now I'm writing up is this component, right? For this subcase, for this case, x is the direction of the loading, which means I decompose fx. And so that is the case. And for the second decomposition, which means that is corresponding is the force Fy. This is Fy, right? So in the second case, the Fy should be in this direction. About this, I do this step by step and not to confuse people. So let me do this again. So basically, this by decomposition, this will decompose into Fx, and this will be decomposed into Y, and then this will decompose into Fz. Okay, and again, everything is in static equilibrium. Okay, and then, so in this way, for this case, the axial loading is defined in the x direction. For this case, the axial loading, the axial direction is the y direction. For this case, the axial direction is the z direction. Per our definition here, I say that the axial direction is the direction where the loading applied. Okay, so right now I simply want to apply this kind of simple scenario to individual cases. Okay, and now furthermore, we divide the loading with the corresponding cross section or the corresponding area is acting on, then we can find is the stress, right? The stress in average is the loading by area. So which means for individual case, that can be equivalent to is like this. X, Y, Z. So that will be equivalent. Again, divide the force by area, that will be the sigma x. Right? Okay, and then for the second case, we have the similar way. So that is X, Y, Z. And then corresponding, dividing the Fy by this cross-section area, and that is the sigma y. So right now for this case, y is the axial directions. And now for the third one, X, Y, Z. And then again, divide the force Fz into by the area, so that will corresponding is sigma z. And keep in mind, the three things still under the superpositions. Okay, so now we do these things individually. For this case, so I'm going to, for individual cases, I'm going to write down the information here. For this case, this is the axial loading, right? The axial loading, we follow these formulas here. The axial loading, we know the axial stress. Divided by Young's modulus, we get is the axial strain. So for this case, sigma x is the axial strain, because right now the axis is axial direction, so that is sigma x divided by E. Sounds good? And sigma y. So right now the x is the loading direction, so that means this material, if you borrow this concept here, the lateral direction will be reduced. So you can imagine if this would be the chewing gum, you stretch it in that direction, well, that meaning the y direction and z direction will be reduced. So that means the strain, we pick up this formula here. The lateral direction, the strain this is a lateral strain equal to minus mu multiplied with the axial strain. Minus mu multiplied with axial strain. Are we okay? And in the z directions, this is the lateral strain. So lateral strain equal to minus mu multiplied with axial strain. So minus mu multiplied with axial strain. Okay? So now we're done for one case. For the second case, the first step is we define which direction is the loading direction is y. So we start from the axial direction. In the axial direction, we have Hooke's law governed by this. So now y direction is our axial direction, so which means this is our axial strain. Axial strain equal to the stress divided by Young's modulus. So this is following this, right? Okay, the key step for individual cases is you have to first identify which